Hello friends, I hope you are doing great wherever you are. It's a beautiful morning here and I hope life is good that side. IBM is here with another episode of Learning Physics, and remember we are dealing with solve the past paper questions that is in AS Physics, that is Physics 9702. This is electricity and DC circuits, and this is going to be actually part 2 of these solve the past paper questions. Do not forget, within these videos, we are going to discuss questions with the current, potential difference, EMF, resistance. Ohm's law will be mentioned many times, electric power and efficiency, the IV characteristic graphs, Kirchhoff's laws will be seen many times, potential dividers, and a lot more that you should expect in these videos. Without wasting any time, I would like to take you to the solved past paper questions or to the document of solved past papers so that we solve them and progress into part 2. Let's move to the document. So this is the document that we have been using, and I think in part 1 we must have stopped on page 373. So in part 2 I want us to move to page 374. The first question: a filament lamp is rated as 30 watts, 120 volts. A potential difference of 120 volts is applied across the lamp. For the filament wire of the lamp, calculate the current. So this is very easy. Current, since we have power, we have PDV as to 120 volts. Then we shall just use the equation of electric power, which is I squared times R, or you could use this could be the same as using I times V. So since I have V and I want I will just use IV. So I is going to be equal to R, sorry, not IV. Okay, I is going to be equal to power divided by V. When I make power the subject in IV, so the power is 30 and V is 120. So when you press your calculator, I think that is a quarter. 30 divided by 120, that is a quarter, which is 0.25. Then the number of electrons passing a point in 3 hours. The time is 3 hours. Remember, charge is equal to IT. That is charge. But we have the current and we have the time. But charge is going to be, because we want number of electrons passing a point, charge is going to be the number of electrons times the charge of each electron. This should be equal to I times T. So total charge is N times E, because N is the number of electrons and E is the charge of each electron. When you multiply, you get total charge. So the number of electrons is going to be equal to I times T divided by the charge of each electron. So this is going to be, the current is 0.25. The time is 3 hours, so we change it to seconds. That is times 3,600. Divided by the charge of each electron is 1.6 times 10 power negative 19. So 0.25 times 3,600 times 3 divided by open brackets 1.6 exponent negative 19. So that is giving us 1.69 times 10 power 22. 1.69 times 10 power 22. Show that the resistance of the filament wire is 480 resistance. Since we know that electric power is I squared R, or electric power is V squared over R, we can use any of those expressions to find the resistance. Let me use the last one. So electric power, I'll make electric power is equal to V squared over R. I'm going to use make R the subject, so R is going to be equal to V squared divided by the power. So this is going to be 120 squared divided by the resistance, divided by the power, which was 30. And when you press the calculator, 120 squared divided by 30, that is 480. So this is 480 ohms. The filament wire has an uncoiled length of 580 nanometers. So the length is 580 and is made of metal. The metal has resistivity of 6.1 times 10 power negative 7 at the operating temperature of the lamp. Calculate the diameter of the wire. So we want to calculate the diameter of the wire. First of all, we know that resistance in terms of resistivity is going to be rho L over cross-sectional area. You and me know that area is equal to pi d squared over 4. So when I substitute for the area here, it becomes 4 times rho L divided by pi d squared. So we want to find the diameter of the wire. We have length, we have resistance, we have resistivity. So I'll make d the subject. So diameter, okay, diameter is going to be equal to the square root. I'm making d the subject. We are all A-level students. Making the subject, that is simple algebra. Making d the subject, I remain with 4 rho L divided by pi times r under square root because d was squared. So now I simply substitute. D is going to be the square root of 4 times rho, which is 6.1 times 10 power negative 7 times the length, which is this one here is going to be 580 divided by 1000, which is 0.58. So L is 0.58 divided by pi times R, which R we got as 480. So we have 4 times 6.1 exponent negative 7 times 0.58 divided by pi times 480 under square root. So that is 3.06 times 10 power negative 5. 3.06 times 10 power negative 5, which is approximately 3.1 times 10 power negative 5 in meters. Okay. Then the potential difference across the resistor is now reduced. State and explain the effect, if any, on the resistance of the filament wire. Potential difference across the lamp is reduced. State and explain the effect, if any, on the resistance of the filament wire. So resistance is equal to PD squared over power. If the power of the lamp has not changed and the potential difference is reduced, it means the resistance automatically reduces. The resistance automatically reduces. Alternatively, we can look at power is equal to IV, so that means the current is equal to power divided by V. If power is constant and the potential difference is reduced, the current increases. If the current increases, it means the resistance has reduced. Therefore, we can simply say that resistance is directly proportional to PD. Resistance is directly proportional to PD. So resistance increases. So resistance decreases. So when the PD across the lamp is reduced, the resistance decreases. Okay. A network of resistors, each of resistance R is shown in the figure here. Calculate the total resistance in terms of R between points A and C. Between points A and C, so it means we have cut off, we have ignored all this other part here. That has been ignored. Between A and C, we only have one resistor of resistance R. Therefore, the total resistance there is going to be the resistance of that resistor, which is going to be R. That is R. Okay. Number 2, or part 2, between B and X. B and X. Between B and X, we have this. This is between B and X. This is X. So between B and X, we have two options. This we can't consider this. We can't consider that because the other end AZ is open. But B to X, we have BCX and we have BYX, and this are in parallel. Between B and X, we have two resistors that are in parallel because they are linked to the same point. They are all linked to point B and they are all linked to point X. So they are in parallel. So therefore, the total resistance is going to be got from 1 over resistance in total is going to be 1 over R plus 1 over R, which is going to be 2 over R. Therefore, R total is going to be the reciprocal, which is R over 2. So between B and X, we have 1 over R total is equal to 1 over R plus 1 over R because they're in parallel. And this is going to give us 2 over R. That means when I get R total, it's going to be the reciprocal, which is R over 2. So this is R over 2, or it is a half of R, a half R. Then A and Z. A and Z. A and Z. So for A and Z, note that, so we are looking at this point and this point here to find total resistance. I want you to note that these two in the bottom are in parallel. They give us a total resistance of a half of R. Then we have this resistor here and we have this one here. These two are in series with the parallel combination. So you have a half R plus R plus R. So we have okay, so we have said that okay, let me first clear off this. Okay, sorry for that. So this is R total will be this was a half R. Check. So a half R plus R, that is going to be a half R plus 2R, which is going to be, this is over 1. So I think this is LCM is 2. So you have that is R plus 4R, which is going to be 5 over 2R. So that gives us 2.5 R. So this is going to be R plus a half R, that is in parallel again, plus R, which we have said is 2R plus a half R, which gives us 5 over 2R. So the resistance here is 5 over 2 R, or it is 2.5 R. Okay. Two cells of EMF E1 and E2 and negligible internal resistance are connected to the network in A as shown. So we have two cells here. The currents in the network are indicated as indicated. They have showed us the direction. Use Kirchhoff's laws to state the relation between I1, I2, and I3. So we look for a junction. So we can say at junction B, You see that I1 is entering, I2 is also coming, I2 is coming, so I'll say plus I2, I3 is leaving, so that is equal to I3. The sum of currents into a junction is equal to the sum of currents out of the junction, so that the algebraic sum of currents at the junction is 0. So I'll simply say I3 is equal to I1 plus I2. That's Kirchhoff's first law, which is a consequence of conservation of charge. Then we want the relation between E2R, I2, and I3 in the loop. B, C, X, Y back to B. So the loop is in here. That is going to be clockwise and anti-clockwise in that direction. So the sum of EMFs, there's only one cell, so the EMF is going to be E2. Because there's only one cell. The EMF is E2. Then the sum of PDs. Remember, if the current is in the same direction as the loop, the PD is positive. If the current is in the opposite direction to the loop, the PD is negative. Okay? So let's see, we have E2 is the only cell. And you notice that the current is in the opposite direction to the loop. The current through the cell is in the opposite direction to the loop. So this EMF is going to be negative. So that negative is going to be equal to the PD across R, the first arrow through which current I2 is flowing. Because the current is in the opposite direction to the loop, this speed is going to be negative I2 times R. Then for the other current, for the other resistor R whose current is I3, you also see that the current is in the opposite direction to the loop. So that will also be negative I3 times R. So the negative literally cancels out, so we have that E2 is equal to I2 times R plus I3 times R. Because the negative is on both sides, it cancels out. So E2 is going to be equal to I2 times R plus I3 times R. Then between E1, E2, R, I1, and I2 in the loop A, B, C, X, Y, Z, A. So that is the upper loop. A, I'm going to change the color so that I have a different loop. It is from A to B to C, X, Y, Z, back to A. So that is the external loop. It is still anti-clockwise. So we ignore the current I3 because it is within the loop. It is inside the loop. So we only take the external loop. We are moving externally. We don't include I3 there. So the sum of EMFs, you notice that in moving around the loop, E1 is the current through E1 is in the same direction as the loop. So E1 is going to be positive. Then when we come to E2, you see that the current through E2 is in the opposite direction to the loop. So this is going to be minus E2. E2 will be negative. Because in moving around the loop, you meet positive before negative. That means the EMF will be negative. Here in moving around the loop, you see negative before positive. So the EMF is positive. So we have finished the only two cells. We have finished the sum of EMFs. Now let's check the sum of PDs. So for this resistor, the current through it is in the same direction as the loop. So the P is going to be positive I1 times R. Let's check for this one also. The current through this one is the same as I1. The current through here is I1 because they in series with this resistor here. So the current is in the same direction as the loop. So this will also be plus I1 times R. Then we have a resistor at the bottom. The current I2 is in the opposite direction to the loop, so that will be a minus. So this will be minus I2 times R. So in other words, if you want, you can factor out, but these two can sum up and they will give us twice I1 times R, then minus I2 times R. So that is the simplification there. Therefore, the sum of EMFs, remember, should be equal to the sum of PDs. The sum of EMFs should be equal to the sum of PDs. So for that reason, we can have a simple expression as E1 minus E2 is equal to the sum of PDs, which we have seen as twice I1 times R minus I2 times R. So that will be our equation. E1 minus E2 is equal to twice I1R minus I2R. A network of resistors, each of resistance R is shown in the figure here. Switches S1 and S2 may be open or closed. Complete figure 7.2 by calculating the resistance in terms of R between points X and Y for the switches in the positions shown. S1 is open and S2 is open. S1 is open and S2 is open. We can't say there is no current flowing. No current can flow through those resistors because S1 is open and S2 is open. Since no current is flowing, we can't say the resistance is zero. Not at all. In that case, we say the resistance is infinity. When both switches are open, when a circuit is open, then the resistance is infinite. If no current can flow, then the resistance is infinite. Then it is infinity. Then S1 is open, but S2 is closed. Let's assume S2 has been closed. So it means this R is out and this one is also out. But these two are in series. So the total resistance here is going to be R plus R because they're in series. So that is R plus R, which gives us 2R. So that means if one is open, S1 is open and S2 is closed, then the resistance is twice R. Then if S1 is closed and S2 is also closed, S1 is closed and S2 is also closed. So it means all resistors are in play. They can be considered. Remember, these two were in series, they gave us 2R. These two are also in series, they will give us 2R. But 2R is in parallel with 2R. That means total resistance is going to be got by combining two parallel resistors. That is, 1 over total resistance in parallel will be equal to 1 over 2R plus 1 over 2R. The LCM is 2R, so this will be 1 plus 1, which is 2. So when we get the reciprocal, you note that 1 over R total is going to be equal to 2 over 2R, and when you get the reciprocal, R total is equal to 2R divided by 2, which is actually R. So if all switches are closed, then the resistance here is going to be simply R. Two cells of EMF E1 and E2 and negligible internal resistance are connected into a network of resistors as shown here. So the network has been shown here. The currents in the network are as indicated. They have showed you the direction of the currents. Use Kirchhoff's laws to state the relation between I1, I2, I3, and I4. Let's see I1, I2, I3, and I4. I1, we can look for a junction. Let's choose which junction. We can choose junction N. I1 is entering junction N, I2 is leaving, I3 is entering, I4 is leaving. So this is I4, this is I3, this is I2, and this is I1. According to Kirchhoff's first law, the sum of currents entering the junction should be equal to the sum of currents leaving the junction. Which currents are entering so that we sum them up? We have I1 plus I3. Those ones are entering the junction N. And which currents are leaving so that we sum them up? That is I2 and I4. Those ones are leaving. So the sum of currents entering a junction is I1 plus I3 should be equal to the sum of currents leaving the junction, which is I2 plus I4. Then the relation between E1, E2R, I3 for the loop NKLMN. NKLMN. So you are moving around like this. NK, you're moving in that direction. That is clockwise. So you will ignore the other part on the right hand side, that is NKQ. You will ignore that part. So we want sum of EMFs, it is only one cell. You notice that in moving around the loop, you encounter minus sign, minus plate, minus terminal, then the positive terminal. So the EMF is going to be positive E1. Then we look for the PDs. There are only two resistors, this one and that one there. So this one, the current through it is in the same direction as the loop because the loop is clockwise. So the PD is going to be I2 times R plus. For this one, the current is still I2. It is in the same direction as the loop, so it will also be I2 times R. Therefore, is there any other cell here? NK. Oh, there is also this one here. So I have to check this again because P is not included. Sorry about that. P is not included, so I'm going to ignore this part in the middle. It is NK, so P is out. It is NK, so the loop is like this. It leaves out P. It leaves out this one and this one here. So the loop is like that. So this is not true. Sorry for that. So, but the EMF remains the same. E1 is positive, but there is now this cell here, NK. There is this cell here, which is if I move from N to K, I meet positive before negative. So the EMF is negative, so that will be minus E2. So this will be E1 minus E2. That is the sum of the EMF should be equal to. The PDs will only have now one resistor R, which is this one here, because these ones are out, they are inside the loop, so they cannot be considered. So the EMF is good. The current through it is I3, but is in the opposite direction to the loop. So this will be a negative. So this will be minus I3 times R. Minus I3 times R. The minus is because the current is in the opposite direction to the loop. You're moving from N to K, but the current is from K to N. So the PD is negative. Therefore, if I simplify this, it can be E2 minus E1 equaling to I3 times R. The negative here can change this. So it becomes E2 minus E1. So this can be E2 minus E1 being equal to I3 times R. Then between E2, R, I3, and I4, the loop is NK, NKQN. N to K, Q back to N. The loop is here. N to K, so it is like that. It is anticlockwise. N to K, Q back to N, that is anticlockwise. Okay, so the sum of EMFs, in that case, we have only one cell and we are moving in the opposite direction to the EMF. Because when you are moving from N to K, you meet positive before negative. That EMF is going to be negative EMF negative 2 equals sum of PDs. The current here is I4 but is in the opposite direction to the loop. I4 is in the opposite direction to the loop. You are moving from NKQN, but the current is from NQK. So the PD is going to be negative I4 times R, but there's another resistor also, negative I4 times R. So it means negative E2 is going to be equal to, is there any other resistor? NKQ. Oh, there's this one here. There's this one here, NK, where the current is I3. So we have the PD here is going to be, the current is upwards, but the loop is downwards. So again, this is going to be minus, this will be minus I3 times R. Okay, so negative E2 is going to be negative. We combine these two to give us twice I4 times R minus I3 times R. The negative cancels so that E2 will be twice I4R plus I3R. The negative has cancelled out. Therefore, the equation is going to be E2 is equal to I3 times R plus twice I4 times R. Okay, define EMF. We have defined EMF several times as the energy transferred from chemical to electrical per unit charge, or the energy transferred from chemical to electrical for every charge which is being driven through around a complete circuit. So this is energy. EMF is equal to energy per unit charge. So the energy transformed from chemical to electrical. Energy transformed from chemical to electrical per unit charge driven around a complete circuit. Energy transformed from chemical to electrical per unit charge driven around a complete circuit. That is EMF. A cell of EMF 1.5 volts and internal resistance 0.2 ohms is connected in series with the resistor X and Y as shown in the figure. The resistance of X is constant and the resistance of Y can be varied. The resistance of Y is varied from 0 to 8 ohms. State and explain the variation in potential difference between points A and B, that is the terminal PD across C. Numerical values are not required. Okay, so we know that EMF is equal to the terminal PD plus the lost volts, which is the current through the battery times the internal resistance R. This is the lost volts. So it means terminal PDV is equal to the EMF minus the lost volts in the battery, lost volts. So we want to explain what happens to the terminal PD. State and explain the variation in the potential difference between points A and B. Remember, the resistance is varied from 0 to 6 ohms. Of course, when the resistance of Y increases from 0 to 6 to 8 ohms, it means the current flowing decreases, which means the current through the battery becomes smaller. And if the current through the battery becomes small, it means the lost volts decreases. Remember, the EMF is constant. If the lost volts decreases, it means the terminal PD is going to increase. As simple as that. Therefore, we are saying the current decreases. The current in the circuit decreases. The current in the circuit decreases as resistance of Y increases. So the current decreases as resistance of Y increases. We have seen that the lost volts reduce as resistance of Y increases. The lost volts reduce. The lost volts reduce as current decreases, or as resistance of Y increases. The lost volts reduce as current decreases. The lost volts will reduce as the current decreases. Why does the current decrease? Because the resistance increases. So if the lost volts decrease and yet terminal PD is EMF minus lost volts, it means the PD across AB increases. So the PD across AB increases. The resistance of Y is set to 6 ohms. The current in the circuit is 0.18 amperes. Calculate the resistance X. So this has been set to 6 ohms and the current flowing is 0.18, and we want to find resistance X. There are several ways of doing this. Number one, we can use the general equation. We know that current through the circuit is going to be EMF over total resistance. So current through the circuit, this is method number one. I will say that current through the circuit, I'll call total current through the circuit, is going to be equal to the EMF divided by total resistance R total. So that means, and the current has been given as 0.18 is equal to the EMF, which is given as 1.50 divided by total resistance. The resistors are in series. I will just add them up. So I'll add resistance of X plus 6 ohms plus 0.2 ohms. We have only one unknown here. So if we solve this, we shall have Rx plus 6.2 is equal to 1.5 divided by 0.18. So 1.5 divided by 0.18, then minus 6.2. So we get this as 2.13 recurring. So resistance X is equal to 2.13 recurring. So this is 2.13 ohms. Alternatively, you can find a terminal PD from the EMF minus the PD across all the other resistors. That is, I will say terminal PD, that is PD across X, not terminal PD. PD across X is going to be the EMF 1.5 minus the PDs across each of the other resistors. For Y, it will be current, which is 0.18 times resistance, which is X. For the internal resistance, it will be 0.2 times the current, which is 6. It will be 0.2 times 0.18. It will be 0.2 times 0.18. So that is going to be the PD across X. I can check this. 1.5 minus 0.18 times 6 plus 0.2 times 6, not 6, 0.2 times 0.18. So that is the PD across X. Then to find the resistance, I will divide the PD by the current, which is 2.1. So then the resistance X is going to be the PD across X divided by the current, which was 0.18 times 6 plus 0.2 times 0.18, then 1.5 minus the answer, that gave us 0.384 divided by 0.18, which gave us 2.13 ohms. Then the PD between points A and B, that is actually the terminal PD between points A and B. So we just subtract the lost volts. The terminal PD, that is AB, is equal to the EMF minus the lost volts. So this is going to be 1.5 minus the lost volts, which is current. Lost volts is V across the internal resistance, which is current minus times small r. So that will be 0.20 times 0.18. So 1.5 minus 0.2 times 0.18, which gives us 1.464 volts. Then the efficiency of the cell. Of course, we know that efficiency is equal to the useful power output over the power input. Useful power output over the total input power. Useful P output or power output over the total input power. Let me write this very well. This is going to be the useful output power over the total input power. But output power is I times the terminal PD. Input power is I times the EMF. So I cancels out. So this will only become 1.464 divided by 1.5. If you want it as a percentage, you can multiply by 100. So that one divided by 1.5. So the efficiency is 0.976. 0.976 or 97.6%. Describe the IV characteristic of a metallic conductor at constant temperature. We know that when the temperature is constant, then resistance is directly proportional to temperature. When temperature is constant, we know that the I current is directly proportional to PD at constant temperature. That means the resistance is constant. If the temperature is constant, I is directly proportional to PD. So that is going to be a straight line. It will not be through it will actually be through the origin because it is I against V. So it will be a straight line through the origin since the temperature is constant. So it's a straight line. It's a straight line through the origin. That one obeys Ohm's law. Ohm's law. Ohm's law is obeyed there. I is directly proportional to V at constant temperature. Then for a semiconductor, the IV characteristic graph would look like this. We know that a semiconductor becomes a conductor when temperatures increase. That means initial at low temperatures, it may not be conducting. And it starts conducting at a certain temperature. But the semiconductor conducts when the PD is in one particular direction because many times a diode is forward biased. So I'll choose a different color. So if we choose that the diode only conducts in the positive, when the PDs are positive, it means in the negative part, this will be 0. And it will not conduct until we have reached a certain voltage in the positive side. And when it conducts, it then conducts rapidly. So the gradient now starts increasing. The gradient of the curve starts increasing like that. So that would be the IV characteristic of a diode or a semiconductor diode. Therefore, to describe this, we shall put in words that the line shows zero current for negative values of V up to a few volts, about a few tenths of volts. This is normally 0.5 volts. So the line shows zero current zero current for negative values of V, for negative values of V up to a few tenths, of positive values of V. up to a few tenths of positive values of V, and then we have a straight line. It's actually supposed to be a straight line here with the increasing gradient, not really a curve. And then actually not a straight line, a curve with increasing gradient. Sorry. Let me put back my axes. And I change my color. I said initially the line shows a horizontal zero current for negative values of V. Then here it is going to curve and it's like a straight line, but not a perfect straight line. Where is my ruler? Okay, something like that. It should have an increasing gradient. It is a smooth curve. So the line shows zero current for negative values of V up to a few tenths of positive values of V, that is up to around 0.2, sometimes it is quoted as 0.5. And then the line has an increasing positive gradient. And then a line with an increasing positive gradient. So when it has conducted initially, it then becomes very easy for a diode to conduct when temperatures increase. In other words, resistance decreases when temperatures increase. So it will then show a line with an increasing positive gradient. Okay. Two identical filament lamps are connected in series and then in parallel. To a battery of EMF 12 volts. So we have them in series and we have them in parallel. Okay. Of course, we know in a series the current flowing is the same, the current through which is the same. We know in parallel the current here is going to be the sum of the current here and the sum of the current plus the sum of the current there. So that will be the total current in parallel. The IV characteristic of each lamp is shown in the figure. Use the information shown in the figure to determine the current through the battery in the circuit of 6.1. The current through the battery in the circuit of in circuit 6.1. So since these are identical, so that means their resistance is the same. So the PD of 12 volts is going to be divided equally because these are in series. So this is going to be 6 volts and this is going to be 6 volts. So the PD is the same. The PD is the same. The PD is going to be equal and to be 6 volts because they're in parallel. So first of all, we note that the PD V across each each lamp is equal to 6 volts. So we look for 6 volts from the graph. Remember, the current through each is the same. So we look for 6 volts from the graph. 6 volts is here. And it corresponds to which current? The scale on the vertical is 2 divided by 10, which is 0.2. So this is 2.2, 0.4, 0.6, 0.8. So the current through each lamp is going to be 2.8. Because the PD across one lamp is 6 volts, then the current is going to be 2.8. Of course, I know somebody will look for 12 and will think the current is 4 amperes. But actually, you get the PD across one lamp and it is 6 volts. If I get the PD across one lamp and it is 6 volts, then I can predict the current. Then in B, the PD across each lamp is 12 volts. The PD across each lamp is 12 volts. And in B, the current, you notice that the current is dividing into I1 plus I2. So if the PD across one lamp is 12 volts, I'll look for the current through one lamp. The current through one lamp is going to be 4. But remember, the current through one lamp is 4. It means I1 is going to be 4 and I2 is also going to be 4. That means the current through the battery is going to be I1 plus I2, which is going to be 8. So here in part 2, we are saying the PD across each is PD across each lamp is PD across each lamp is 12 volts. So the current for each lamp, is 4 amperes from the graph. So total current is going to be 4 plus 4, which is equal to 8 amperes. So the current here is 8.0 amperes. Then calculate the total resistance in the circuit of figure 6.1. Figure 6.1, they are in series. So resistance of one lamp, we can find the resistance of one lamp. Resistance of one R of a lamp is equal to the PD across one lamp is 6 divided by the current, which is 2.8. So we are using R is equal to V over I. So the the resistance of one lamp is 6 divided by 2.8, which is 2.1 times 10 power, 2.14, that is repeating. But remember, there are two lamps in series, so total resistance is going to be the sum. So total resistance is going to be the sum, or we multiply 2 by 6 over 2.8. So 2 times 6 divided by 2.8, which is 4.28 or 29 or 4.3. So this is going to be 4.3 ohms. Then in circuit B, we have the current in each, or we can even use the total current, but we have the current in each as 4 ohms. So you can find the resistance of a lamp. R of a lamp in B is going to be the PD is across one lamp is 12 and the current is 4 ohms, which means this is going to be 3 ohms. But remember, they're in parallel. If they're in parallel, then 1 over R total is equal to 1 over 3 plus 1 over 3, which is 2 over 3. So we get the reciprocal. So 1 over R total is equal to 2 over 3, which means that R total is going to be 3 over 2, which is 1.5. So the resistance here is equal to 1.5 ohms. The resistance there is 1.5 ohms. Alternatively, you can use a simple method. Resistance in parallel is going to be the PD in parallel over total current entering in parallel. Total current I total, that is going to be 12 divided by total current, which is 8. 12 divided by 8, which gives you 1.5. Calculate the ratio power dissipated in the lamp in the circuit of figure 6.1a over power dissipated in the lamp in the circuit of figure 6.1b. So we know that power is equal to IV, or you can use power as V squared over R because you have V and R, or you can use I squared R. I'll use the simplest. So the ratio is going to be for circuit 1. The current is 6 because we're looking at just one lamp. The PD is 6 for one lamp and the current is 2.8. PD is 6 for one lamp and the current is 2.8 divided by 4B. The PD across one lamp is 12 and the current across one lamp is 4 amperes. So we have 6 times 2.8 divided by 12 times 4. So the ratio is 0.35. A cell X of EMF 1.5 volts and negligible internal resistance is connected in series to 3 resistors A, B, and C as shown in the figure here. So you see A and B are in parallel. If you want total resistance here, you can even find it. Product over the sum. Product over the sum, that is 6 times 3 over 6 plus 3, which is 18 divided by 9, which is actually 2 ohms. That is total resistance in parallel, it is 2 ohms. Resistors A and B have resistance 6 ohms and 3 ohms respectively and connected in parallel. Resistor C has 4 ohms and is connected in series with a parallel combination. Calculate the current in the circuit. So we want the current, we can find the total resistance like we have said. So to find the current in the circuit, we know that current is going to be equal to the EMF over total resistance. EMF over total resistance. Let's first find the total resistance. We have already said that resistance in parallel, 1 over the resistance in parallel was equal to 1 over 6 plus 1 over 3, which is equal to, or which implies that 1 over resistance in parallel. This algebra disturbs me, it wastes a lot of time. Okay, let me just do it. LCM is 6. 6 divided by 6, that's 1, so that's 1 plus, this is 2, that is 3. So this gives us 2 over 6, which is 3 over 6. That means resistance in parallel, R in parallel is 6 over 3, which is 2 ohms. Or product over sum, like I had done before. That is R in parallel. This is R in parallel, not R total. Then R in parallel is in series with another resistor which is of 4 ohms. So we sum up. So it means total resistance is going to be the sum. R total will be equal to 2 ohms plus 4 ohms, which is equal to 6 ohms. Then now the current is equal to the EMF. They gave us the EMF as 1.5. So that will be 1.5 divided by the total resistance, which is 6. 1.5 divided by 6, that is a quarter, which is 0.25. Okay, number 2, part 2. Then the current in resistor B. The current in resistor B. So we have the total current. That total current is flowing through C, which is 0.25. So it means we need the PD across the parallel combination, We can first get the PD across C. We subtract it from 1.5. The balance is the PD across A or B. So the PD across C is going to be the current, which is 0.25 times the resistance, which is 4. That is the PD across C. When we get the PD across C and subtract it from 1.5, then the balance is the PD across A. It is the PD across B because they're in parallel. Therefore, we are saying that the PD across B is equal to 1.5 minus the PD across C, which is 1.5 minus PD across C is the resistance, which is 4 times the current, which is 0.25. And this gives us 1.5 minus, open brackets, 4 times 0.5, 0.25, which is a half. A half is 0.5 volts. That is the PD across B. We know the resistance B, so without wasting time, I is equal to V over R. V is 0.5 and R is 3.0. Is that the resistance for B? Yes, 3.0. So 0.5 divided by 3, you get 1.6, which is 0.1666 recurring. So this is 0.167 or 0.17. 0.167. Then the ratio power dissipated in resistor B over power dissipated in resistor C. So we have earlier on seen that power can be got from I squared times R or IV, or we can use V squared over R depending on what you want to use, whichever is easier for you. So resistor B, we have the resistance, but of course we don't have the current. It means we would have again to calculate the current, so I will not use that one. I will use one with the V and R because I will not need to. Oh, I have the current in B. That means I have the current in. It means I have the current in C, because the current in C is the total current, and the current in B I have found it here. So still I can use that, or I can use potential differences. Let me start with one, which is of V. So the ratio will be equal to the PD across B squared over resistance of B divided by the PD across C squared divided by the resistance of C. Let me substitute. PD across B is equal to 0.5 squared. Resistance of B, the resistance of B was 3 divided by, now I will change this to multiplication and I get the reciprocal. Resistance of C is 4 ohms. Resistance of C is 4 ohms divided by PD across C, which we got here. It is 4 times 0.25. 4 times 0.25, what does that give us? 4 times 0.25, which is 1. So that is 1. PD across C, which is 1 squared. So we can check this with our calculator. 0.5 squared times 4 divided by 3. So we get 0.33 recurring. So this is 0.33 recurring. That's method number 1. Method number 2, I can use the currents and maybe the resistances, or the current and the PDs. Let me only use the current and the resistances. So method number 2, this was method number 1. The ratio will be I. The ratio will be equal to I of B squared times resistance of B divided by I of C squared times resistance of C. I of B is 0.167 squared times resistance of B, which is 3, divided by I of C, which was 0.25 squared times resistance, which is 4. You can check. gives us the same answer. 0.167 squared times 3 divided by 0.25 squared times 4. That is 0.33. But this method will give you a more exact value because we are only rounding off on the final answer. This method will round it off the current. Nevertheless, both answers will be correct. The resistors A and B, A, B, and C are in B are wires of the same material. That means they have the same resistivity rho because they are from the same material and have the same length L. So L is the same. Explain how the resistors may be made with the different resistances. So we know that resistance of a wire is equal to rho L over A. So they have the same rho, they have the same L. What is remaining is changing the area A. And how do we change the area? We can use wires of different diameters. So we can use wires of different diameters to change the resistance. So use wires of different diameters. Wires of different diameters or cross-sectional area. Use wires of different cross-sectional areas, so they will have different resistances. Then calculate the ratio average drift speed of the charge carriers in resistor B over average drift speed of the charge carriers in resistor C. Remember, they have the same resistivity, they have the same length. So I will use the simple formula for velocity for current. I is equal to never. My students normally use never. They call it never because it's easy to remember. So it means the drift velocity V is going to be I divided by N E times cross-sectional area. Okay, so let's now just come up with the two equations for the ratio. So the ratio is going to be equal to drift speed of B over drift speed of C, which is going to be the current in B divided by, of course, N will be the same, E will be the same. So this is going to simply be current let's say current in B over NE, because they are from the same material, NE times area of B, then divide by, I'll get the reciprocal. So NE times area of C, I've got the reciprocal for the same equation, divide by the current of C. So NE has cancelled out. So it means the ratio is now going to be equal to I in B divided by I in C. Then times the ratio area of C divided by area of B. Remember, we can find area from resistance. So somewhere here we note that the area is equal to resistivity times L over resistance R. So this is going to be equal to I of B over I of C times. I'm now substituting the areas. For C to be resistance, the resistivity is the same, the length is the same over. For C, the area of, the resistance of C, this will be R of C, divided by, for B, its area will be resistivity times L over resistance of B. I'm again simplifying. You notice that rho L cancels out. So I will have IB over IC times. In the brackets, I have rho L over RC times, I get the reciprocal RB over rho L, and rho L cancels out. So in other words, this simplifies to IB divided by IC times RB divided by RC. So that is actually the ratio that we need. This algebra it can be simplified in a short time, but I just wanted to show you, especially the non-mathematicians. So therefore, the ratio we want, RB over VC is going to be equal to IB over IC times RB over RC. If you know relations, you just know you can easily remove those which are constants and just arrive at this expression in a very short time. That's why you see the marks are 2, because it is supposed to be very short. So this is going to be equal to 0.167 squared for B over 4C, which was 0.25. This is not squared. Then times resistance of B, which was 3, over resistance of C, which was 4. So we have this and we have that. So I'll just say 0.167 times 3 divided by 0.25 times 4. That is 0.501 or 0.50. Okay. A cell of EMF 1.5 volts and negligible internal resistance is connected in parallel with the cell X in the figure with their positive terminals together. State the change, if any, to the current in cell X. So we now have, we had a cell X in the figure. Let's go back here to the diagram. They've connected another cell across X. It also has 1.5 volts. The cell of EMF 1.5 volts and the negligible internal resistance is connected in parallel with the cell X in the figure with their positive terminals together. So the positive terminals are together and the negative terminals therefore will be together. State the change, if any, to the current in cell X. Of course, if the two cells are connected together, the total EMF is going to remain 1.5, but each cell is actually going to contribute 0.75, half of 1.5. That means the PD across the cell is going to reduce, or the PD supplied by the cell is going to be reduced to half, which means the current through the cell is also going to reduce by a half, because some current is actually going to take the other path. So therefore we can say the current is going to be halved. The current is halved. The current is going to be halved, or it changes, or the current changes from from 0.25 that we had before, 0.25 amperes, to a half of that is 0.125 amperes. How do we see that? Now current is going to be 0.75 divided by the resistance, which is 6, which is giving us 0.125. Then the resistor C. Resistor C, of course, for resistor C, there will be no change in the current. Here there will be no change. No change in the current. Because I mentioned and said, when they are connected in parallel, each is contributing 0.75 volts. But the total output EMF is still going to be 1.5 volts. So this brings 0.75, the other one brings 0.75, so that the total is 1.5 given to the external circuit. That means the current in C will remain 0.25, not because the resistance, total resistance outside has remained the same. However, the advantage of this, remember, each cell contributes a small amount of its energy, so the two cells will take a long period of time to dry out, or to be drained out, or to lose all their energy, which wouldn't be the case in series. In a series, they will give more energy, but they drain out in a short period of time. So for resistor C, since the total output terminal PD is still 1.5, it means there will be no change in the current. The battery of EMF 14 volts and negligible internal resistance is connected to a resistor network as shown in the figure here. Okay, R and R2 are fixed resistors of resistance 6 ohms and 12 ohms respectively. R3 is a variable resistor which can be varied from 0 to 24. Switch S is closed. So we have closed switch S, which means total resistance includes these ones in parallel. Calculate the current in the battery when the resistance of R is set at 0. When this is 0, the switch is closed. It means total resistance is simply going to be want the current in the battery when the resistance of R3 is set at 0. R3 is set at 0, so we know that V is equal to I times R, or we shall use EMF is equal to I times R. So in this case, because R3 is set to 0, remember the switch is closed and R3 is set to 0. So it means the PD across R3 is going to be 0. The PD across R3 is going to be 0. Remember, the PD across R3 is the same as the PD across R2 because they're in parallel. If R3 is set to 0 and the switch is closed, R3 is set to 0 and the switch is closed, the PD across R3 is going to be 0 times the current I, which means it will be 0. But remember, R3 is in parallel with R2. So it means the PD across R2 will also be 0. Therefore, the total current in the circuit will simply be the current through R1. So total current I is going to be V over R, which is going to be 14 divided by R, which is going to be 6.0. Somebody will say, but why don't we include R2? You can try to include it, because if this is 0, remember they're in parallel. Total resistance in parallel will be equal to 0 times R2 divided by 0 plus R2. So it means the resistance here is going to be 0 for that circuit, for that part. So that means the current flowing through the battery is only the current through R1. So this is going to be 14 over 6, which gives us 2.33. 2.33, I guess. 14 divided by 6, I think it is 2.33. Yes, 2.3 recurring. This is the most complex question here, so that is 2.33. Because many of us will not realize that when this one is set to 0, it means there is no resistance here. There will be no resistance here. Therefore, the current flowing can be obtained, all the PD of 12 volts is across R1. That is the only most important part of that question. Then at 24 ohms, at 24 ohms, PD across So when we put this at 24 ohms, now the resistance changes. Resistance in parallel will be equal to 12 times 24 over 12 plus 24. That is the resistance in parallel. And I think that is 12 times 24 divide by 12 plus 24, which gives us 8. So that is 8. That is in part is 8. Total resistance we sum up. R total will therefore be 8 plus 6, which is equal to 14 ohms. So it means the current, which is equal to PD, that is the current which is equal to EMF over total resistance is going to be 14 over 14, which is equal to 1 ohm. Then use your answers in B Roman 1 to calculate the change in the total power produced by the battery when the resistance of R3 is changed from 0 to 24. We want to calculate the change in the total power produced by the battery. We note that power is equal to IV, or since we are looking at the battery, power is going to be E times I. So remember the initial current is 2.33 and the final current is going to be 1.0 amperes. So let's find the change in power. Change in power is going to be the first, we start with the V or EMF is 14 times, should I use 2.33 or I use 14 over 6? Okay, you just use 2.33, that is initial power, minus the final power, which is 14 times 1.0. So we just put this in the calculator, 14 times 2.33 minus 14, which gives us 18.6. So this is going to be 18.62 or approximately 19. So this will be 18.62 or approximately 19. Switch S in the figure is now opened. Okay, now when it is open, the case changes, the scenario changes. Resistors R1 and R2 are made from metal wires. Some data for these resistors are shown here. Determine the ratio average drift speed of free electrons in R1 over average drift speed of free electrons in R2. So what data has been given? They have given us cross-sectional areas and the number of free electrons per unit volume. So we can now find the average drift velocity. Remember, current is equal to never, I is equal to never. That means the drift velocity V is going to be equal to the current I divided by area N times the charge E. Okay, let's now find a ratio. By the way, do you notice that I1 is going to be the current in A, the current in R1 is the same as the current in R2 when the switch is opened. When the switch is opened, R1 and R2 are going to be in series. When the switch is opened, R1 and R2 are going to be in series in that case. When the switch is opened, R1 and R2 are in series, so the current through R1 is the same as the current through R2. So I will not bother about the current. I'll write here that the current through R1 is equal to the current through R2. I'll just call it I. Okay, now let's find the ratio. So the ratio will be equal to drift velocity through R1 over drift velocity through R2 will be equal to, for R1, the current is I, divided by the area, I'll call it A1. Okay, I'll call it, the area is A, times N, then times of course the charge of the electrode is the same E. That is for R1. Divide by, for R2, the current is I because they're in series. The area is 1.8 A, then times N, the number of free electrons per unit volume is 0.5 N, then times E. So I has cancelled. We just get the reciprocal here, I over, put equal sign so that looks nice. So the ratio equals I over A N E times the reciprocal 1.8 A times 0.5 N times E divided by I. So I want to show you that this cancels out. I has cancelled, A has cancelled, N and E have cancelled. So I remain with only 1.8 times 0.5, which is a half, and that is half of 1.8, which is 0.9. So this is 0.9. 1.8 times 0.5, that is 0.9. So the ratio is 0.90. Then a battery is connected in a parallel with two lamps, A and B, as shown in the figure here. I want you to note that the lamps are in parallel, so the total current I is going to be divided here into IA plus IB. However, they have the same PD. The PD across the lamp is the same. Okay? The battery has EMF 6.0 volts and the internal resistance R. The IV characteristic of lamps A and B is shown here. The potential difference across the battery terminal is 6.0 volts. That is the terminal PD. So the terminal PD is 6. That is going to be the PD across AB. PD across A is the same as PD across B, and they have told us it is 6.0 volts. So just look for it from the graph. 6.0 is going to help us to find the current in each bulb, each lamp. So the PD across is the same, so I will draw a line through all these two. To be able to find the current in A, I will get the current in A from here. I will get the current in B from here. So the current in A is going to be, the scale here is 0.01. So this is 1, 1, 1, 2, 1, 3, 1, 4. So this is 0.14. Then here 1, 2, 3, 4, 5, 6. So this is 0.26. So remember, the current divides, so the total current is the sum. So we have seen that the PD across A is the same as the PD across B. So the current in the battery, no, they said use the figure to show that the current in the battery is 0.4. So the current in the battery is equal to current in A plus current in B, which is 0.14 for A plus 0.26 for B. Let's check. 0.14 plus 0.26, that gives us 0.4 amperes. Then calculate the internal resistance R of the battery. Since we now have the battery current, the current of the battery, we know that EMF E is equal to the terminal PD minus the lost volts. So the EMF is equal to 6.8 minus the terminal PD, which is, equals to terminal PD 6.0 volts minus the lost volts, which is I times small r. So we want small r. So sorry, this is supposed to be plus, not minus. So it means 6.8 minus 6, that is 1.8, is equal to current in the battery 0.4 times small r. So I'll just say 1.8 divided by 0.4, which is, I think that is it 4.5? Did I subtract correctly? 6.8 minus 6. So sorry, 0.8. how did I get 1.8? Normally the internal resistance is supposed to be very small. That's how I'm able to see that I made a mistake. That is 0.8. So 0.8 divided by 0.4, that is going to be 2. So I think R is going to be 2 ohms. Determine the ratio resistance of lamp A over resistance of lamp B. Remember that the resistance is equal to V over I. Remember they have the same PD because they're in parallel. So the ratio is equal to resistance of lamp A over resistance of lamp B, which is equal to 4A. The PD is 6.0. The current of A is 0.14. Divide by 4B. The PD is 6.0 and the current is 0.26. So this is going to be the same as 6 divided by 0.14. Okay, I don't want to do that. I just want to simplify at once. So I will just have two brackets. 6 divided by 0.14. Again, divide by, open another bracket, 6 divided by 0.26. So that's 130 divided by 7, which is I placed here 60 instead of 6. So that is 1.86. 1.86. Then determine the total power produced by the battery. Of course, power produced by the battery is EMF times the current, or I squared R, or you can use V squared, I squared R, or you can use V squared over R. So the first one, the easiest, is going to be EMF is 6.8 times current, which is 0.4. 6.8 times 0.4, 6.8 times 0.4, which is 2.72. Or you can check with the second method, that is I squared is 0.4 squared times R. That means we'll have to find the total resistance. That means you have to find the total resistance, which involves internal resistance plus the resistance of each of the others. Let's check. Total resistance, or by the way, total resistance can still be EMF over total current, which is 6.8 divided by 6.8 divided by 0.4, that is 17. So that is total resistance is 17. And when you press your calculator, 17 times 0.4 squared, that is again 2.72. You can check the other one. So you can either use this or you do that, or you can use V squared over R, where V is PD, which is EMF, which is 6.8, and R is total resistance, which is 17. It gives you the same answer. Then determine the efficiency of the battery in the circuit. Efficiency is simply going to be equal to power out over power input. So power out is going to be I times V. Power input is going to be I times E. I cancels, so this is going to be 6.0 divided by 6.8. 6.0 divided by 6.8, and that is 0.88. 0.88. 0.88. 6 divided by 6.8. 0.882. that same figure repeats itself. So it's approximately 0.88 or 88%. An electric heater has a constant resistance and is rated 1.2 kilowatts and 230 volts. The heater is connected to a 230 volt supply by means of a cable that is 9.2 meters long as illustrated here. So we can see the illustration. So we see that there are two copper wires that make up the cable. So there are two, this one and the other one. There are two copper wires, note that very well. And each has a cross-sectional area of that cross-section of that diameter, and the resistivity of copper is that. So it means it's like we have two resistors here, and because they are joined to the other end like this, they are in series. Yeah, it's like having two resistors in series. Okay. Show that the resistance of the heater is 44.1 ohms. So they have given us the power, they have given us the PD. So we know that power is equal to V squared over R, which means that the resistance can be got from V squared divided by the power. So V is 230 squared divided by the power, which is 1200, because it is 1.2 kilowatts. So we simplify this, 230 squared divided by 1200, which is 44.08, which is approximately 44.1 ohms. Alternatively, we can use another method. You can first find the current and then use R is equal to V over I. Of course, current will be equal to the power over V. Then again, use R is V over I, but that is the same thing. Then the total resistance of the cable is 0.492. Total resistance of the cable. Remember, there are two copper wires forming the cable. So first of all, we know that resistance is equal to rho L over cross-section area. They gave us the diameter. We know that area is equal to pi d squared over 4. So this is going to be 4 rho L over pi d squared. Let's first substitute this. Let's substitute this. So this is going to be 4 times the resistivity, which is given as 1.7 times 10 power negative 8 times the length. The length is 9.2 meters for one copper wire, but remember there are two. There is one at the top and one at the bottom. They are joined in series. So the total is going to be, we are multiplying this length by 2. So this is going to be times 2. So that would be 9.2 times 2, total length. Then divide by pi times the diameter. The diameter is given as 0.9 millimeters. We shall change it to meters, so that is 0.9 times 10 power negative 3, and that should be squared. So 4 times 1.7 exponent negative 8 times 9.2 times 2. Divide by, in the numerator we have pi into bracket 0.9 exponent negative 3, but this is squared. So we get 0.491 0.4916 0.4916169, or approximately 0.492 ohms. The current in the cable and the heater is switched on. Determine to 3 significant figures the power dissipated in the heater. Power dissipated in the heater, we know that power can be I squared R. So power is equal to I squared times R, and we know that I is going to be V over I can be V over R, because we have the resistance of the heater as 44.1 ohm, and we have the PD across the heater as 230. The resistance is 44.1 ohms, and we have the PD as 230. So I will simply say this is going to be equal to, let me say, and I is equal to V over R, which is 230 divided by 44.1. So the power is going to be 230 divided by 44.1. Is it 0.1 or 0.6? The current in the cable and the heater is switched on. Determine 3 significant figures the power dissipated in the heater. Okay, so the resistance of the heater alone was 44.1, but the resistance of the cables we have seen as it is 0.492. So we are going to get the total resistance here to get the power dissipated in the heater. So this is going to be 44. The current is going to be 44.1 plus the other resistance is 0.492. That is the total. To find the total current, the current will get PD over total resistance, and total resistance is 44.1 plus 0.492. So the power is going to be equal to, so this will be, I think this is 44 point, that will be 592, but this should be squared times the resistance of the heater, which is 44.1. Yes, so that is 230 divided by total resistance. This is 44.592. That one is current, but should be squared. Then times 44.1. That is the resistance of the heater, which is equal to 1173.22. 1173.2. I will simply write 1170 to 3 significant figures as required. Okay. State 2 disadvantages of connecting the heater to the 230-volt supply using a cable consisting of thinner copper wires. Thinner copper wires. We know that resistance is directly proportional to length. Resistance is directly proportional to temperature. Resistance is inversely proportional to area. If the copper wires are thinner, it means the cross-section area is smaller. And if the cross-section area is small, it means that the resistance is going to be higher. So if the resistance is higher, remember power is equal to I squared times R. A higher resistance means that the power dissipated is going to be more. The power loss is going to be more. So it means we expect more power loss. More power loss in the cable. More power loss in the cable as the current is going to be lower. Of course, if the resistance is high, it means the current is lower. And if the current is lower, we expect more power loss in the cable as the current is going to be lower. Number 2, if there is more power loss in the cables, it means the power dissipated in the heater is going to be less, and yet we need the heater to have more power dissipated. So there will be less power dissipated in the heater because of a small PD across the heater. There will be less power dissipated in the heater. There will be less power dissipated in the heater because of a smaller PD across the heater. Since the current is now smaller, the PD across the heater will be less. There will be less power dissipated in the heater, or a smaller PD across the heater. Of course, since there is more power loss in the cables, as the current flowing is lower, it means the cables could become heated up and maybe melt. I can add another one. More power loss in the cable as current is lower. So the cables or the cable could become heated up. Could become heated up and melts. The cable could become heated up and it melts there and then. Okay, the variation with the temperature of the resistance RT of a thermistor is shown in the figure here. So we have variation with the temperature of a thermistor. So that is the figure. We can have a look at it. Okay, the thermistor is connected into the circuit as shown in the figure. The battery has EMF of 9 volts and negligible internal resistance. The voltmeter has infinite resistance. That means no current flows through it. For the thermistor at 22.5 degrees Celsius, calculate the total resistance. Calculate the total resistance between points A and B. So at 22 degrees Celsius, let's look for 22 from the graph. At 22 degrees Celsius, so the scale here is 5 divided by 10, that is 0.5. So that is 21, 22.5. That is there. So 22.5 is here. Let's check the resistance from the graph. So at 22.5 degrees Celsius, what is the resistance? So from the graph, the resistance is, here it is, the scale is 0.1, 1, 2, 3, 4, 5, 6. So that is 1.6 kilo ohms. 1.6 kilo ohms, that's 1,600. So the resistance here is 1,600 at 22 degrees Celsius. So determine the total resistance between points A and B. So remember, no current flows through V, so that one we shall ignore it. And A, the thermistor and 1.6 will be in parallel. So we shall find total resistance. So resistance of the thermistor is 1,600. Resistance of the thermistor is 1,600 ohms. Then total resistance. Because they're in parallel, we just do product 1,600 times 1,600 over the sum, which is 1,600 plus 1,600. I think that is 800. 1,600 times 1,600 divided by 1,600 times 2. That is 800. Then calculate the reading of the voltmeter. So we have total resistance of that. The PD across AB is going to be the same. So I will use potential dividers to find the PD across AB. I will use one of the resistors of the PD across the total resistance of 800. So PD across a certain resistor is equal to total resistance, that resistor over total resistance, that resistor over total resistance times the voltage supply, Vs. So PD across 800 is going to be, the resistance is 800, divided by total resistance, which is 800 plus, there's a resistor here, which is 1200, 1200, then times the voltage supply, which is 9.0. Alternatively, we can find total current, because you want a PD across AB, and V is equal to I times R, where R is 800. So you need I. So I is going to be equal to the EMF over total resistance, R total, where total resistance will be this one, 1200, plus this one, which is 800. That will be total resistance. And the EMF is 9. Total resistance is going to be 2000. So you multiply now 2000 times R, which is the same thing as we are doing here. So this will be 800 divided by 2000 times 9, which is 3.6. So this is 3.6. Alternatively, you could find the PD outside, the PD of across this, and subtract it from 9 volts. What do I mean by that? I could say the PD across 1.2 kilo ohms is equal to 1.2, which is 1200, over total resistance, which is 800, plus 1200 times 9. I get that PD, which would be 1200 divided by 2000 times 9, which is 5.4. So it means now the PD across AB, which is the reading of the voltmeter, will be 9 minus 5.4, which is equal to 3.6 volts. So you can use that method. Okay, the temperature of the thermistor is changed. The voltmeter now reads 4 volts. Determine the total resistance between points A and B on the figure. The voltmeter now reads 4 volts. That means the PD across AB is now 4 volts. So we want to determine the total resistance between points A and B. So first of all, we shall need the current. Let's first of all find the PD across 1.2 kilovolts. The PD across 1.2, the 1.2 kilovolts. So the PD across 1.2 kilo ohms, because the one of the voltmeter is 4 volt, the reading of the voltmeter is 4 volts. That means the PD outside the parallel combination is going to be 9 minus 4, which is equal to 5.0 volts. That is the PD outside. That is 9 minus 4. That is now the PD across the resistor, which is not in parallel. So we can find the current through it. We can find the current through it so that we find the total current. That current is going to be total current because it is in series with the battery. So we shall simply say that the total current is going to be the PD across 1.2, which is 5, divided by the resistance of 1.2 kilo ohms, that's 1200. This is now the current. That current is going to be the total current entering this junction here. So we can now find the resistance from PD across AB over the total current entering AB. So R is going to be V over I. V is 4.0 over the current entering, which is 5 divided by 1200. So we have 4 divided by 5 divided by 1200, which is 960. So this is 960 ohms, which is, by the way, the same as 0.96 kilo ohms, because I may need that, 0.96 kilo ohms. Then determine the temperature of the thermistor. So total resistance is 0.96. That is total resistance in parallel. Resistance in parallel is 0.96 kilo ohms or 960 ohms. But remember, 1 over resistance in parallel is going to be 1 over the resistance of the thermistor, which I'm going to call RT, plus 1 over, the other one is 1.6. So 1 over 0.96 is equal to 1 over R of the thermistor plus 1 over 1.6. So let me find the resistance of the thermistor. 1 over resistance of the thermistor will be 1 over 0.96 minus 1 over 1.6. These are in kilo ohms, remember. So I'll just say open brackets, 1 divided by 0.96 minus, open another bracket, 1 divided by 1.6. So to get the resistance of thermistor, I get the reciprocal. So R thermistor is the reciprocal of 12 over, that will be 12 divided by 5. 12 divided by 5, which is 2.4. So the resistance of the thermistor is 2.4. Now I can find the temperature. This is kilo ohms, remember. Resistance of the thermistor is 2.4 kilo ohms. So from the graph, I can find the temperature. So resistance is 2.4. This is 2.1, 2, 3, 4. 4 is there. So I'll draw a line to find the temperature. What is happening to this pen? So I think this is going to be 11 because the scale on the x-axis was 5 divided by 10, 0.5. So there are two small squares. I think that is 11 degrees. So the resistance there is going to be 11 degrees. So the answer there is, the temperature is going to be 11 degrees, corresponding to 24. So the temperature corresponding to 2.4 kilo ohms from the graph is 11 degrees Celsius. You can verify for yourselves. Okay. A student suggests that the voltmeter reading up to 10 volts could be calibrated to measure the temperature. Suggests two disadvantages of using a circuit with this voltmeter for the measurement of temperature in the range 0 degrees Celsius to 25 degrees Celsius. Of course, if the voltmeter reading can be calibrated up to 10 volts to measure temperature, it means only a small part of the scale is going to be used, because we have seen that this could be having a small sensitivity, since a wide range of temperatures could or a very small range of temperatures could not be measured. Temperatures below 0 degrees Celsius could not be measured, and a small change in temperature may not easily be measured. If a student suggests that the voltmeter reading up to 10 volts could be calibrated to measure temperature, it means only a small part of the scale is going to be used, as we have seen above. A small part of the scale is going to be used, as we have seen in this illustration here. Number two, We notice also that temperature does not vary linearly with the PD. So it means the scale is going to be non-linear. That is also a limitation. In fact, is the most important limitation. So number one, variation of PD with the temperature is non-linear. We have seen it is not even a straight line. Variation of PD with the temperature is non-linear. Number two, only a small part of the scale is going to be used. Only a small part of the scale is going to be used. Only a small part of the scale is used. Let me just say is used. What does that imply? i.e., it has a small sensitivity. That thermometer, our thermometer, which has been calibrated by using voltage, will have therefore a small sensitivity. Okay. A lamp is rated 12 volts, 60 watts. 36 watts. Calculate the resistance of the lamp and its working temperature. At its working temperature. So power is equal to V squared over R, which means resistance is going to be V squared divided by the power, which is going to be 36 squared divided by 12. 36 squared divided by 12. It is V squared over V is 12. So that is 12 squared divided by 36. So that is 4 or 4.0. On the axis of the figure, sketch a graph to show the current, voltage, characteristic of the lamp. Mark an appropriate scale for current on the y-axis. So the current goes up to a 4, so I will just choose a simple scale. So let's say this is 0, 1, 2, 3, 4, 5, 6, and I have 4 divided by, or 6, 4 divided by, okay, I'll just use 1.56 divided by 4, that is 1.5, so this is going to be 1.5. No, let me just use every two marks. This is 1.5. This is going to be 3.0, and this will be 4.5. I think that is fine. Okay, then on the x-axis we have 6, 12. That one has been marked for us. So we are now going to, they said mark an appropriate scale for current on the y-axis. Okay, and then we are going to sketch a graph to show the IV characteristic of the lamp. Calculate the resistance of the lamp at its working temperature. This is a filament lamp. At 12 volts, the resistance is actually going to be 4. What is the current? I is equal to 12 over 4 because I is equal to V over R. So at 12 volts, the current, this is going to be 3.0 amperes. So at 12 volts, I'll put a ruler to sketch this correctly. At 12 volts, I think at 12 volts, use a ruler to estimate this correctly. So this is around this point here. Okay, so at 12 volts, the current is 3. You can even check at 6 volts. at 6 volts, at 6 volts, at 6 volts, the current is going to be 6 over 4, which is 1.5. So at 6 volts, 1.5 is around here. Of course, at 0, that will be 0. So this is not a straight line, but to be a curve. To be a curve which becomes almost okay. So that is going to be a curve. Let me first erase this. It will start as a straight line. When the voltage is small, of course, it's supposed to be a straight line, and then it curves. Yeah, it then curves. When the current increases beyond for a filament lamp, then it starts curving. Yes, so it will be a straight line from the origin, then it curves to show that as the PD increases, the point comes when the current, of course, the bulb starts glowing when the current is constant. That's when the temperature is very high. So the graph is crossing 12 volts, 3 amperes. The line passes through that. It starts as a straight line initially, then it curves to be a straight line from the origin, which then curves because the current flowing becomes constant as the resistance tends to infinity. Okay. Then some heaters are labeled 230, 1 kilowatt. The heaters are have constant resistance. Determine the total power dissipated for the heaters connected as shown in each of the diagrams shown below. Okay, they have 240, power is 1 kilowatt. Okay, so part 1, the resistors, the heaters, are they identical? Let's assume they are identical. They have a constant resistance. So let the resistance of this be R and this is R. The in parallel total resistance here is going to be R times R over R plus R, which is going to be R squared over 2. So total resistance here, R total, is going to be R squared over 2R, which is equal to R divided by 2. Then power is equal to V squared over total resistance, which will be V squared divided by total resistance, which is R over 2, which becomes twice V squared over R. Remember, V squared is power, which power was 1 kilowatt. Power was 1.0 kilowatts. So this is going to be twice, 2 times 1.0 kilowatts. So the answer here is going to be 2.0. Then here they are in series. So R plus R, the resistance here is twice R. Total resistance is twice R. So power is going to be equal to V squared. Power is going to be V squared, where V is the total voltage over total resistance, which is going to be 2R. So total power dissipated here is going to be a half of V squared over R. Remember, V squared over R was the initial power, which is a half times 1.0 kilowatts. So that would be 0.5 kilowatts. Then for the second one, these are in parallel. Total resistance is going to be R over 2, as we have seen. But then this is in series. So total resistance is going to be R over 2 plus R, which becomes Total resistance here is going to become a 3 over 2R. Then total power dissipated is V squared over total resistance R total, which is going to be V squared divided by total resistance, which is 3 over 2R, which is going to be the same as 2 over 3 into V squared over R. And this is, remember, that was the power. So this becomes 2 over 3 times the initial power, which is 1.0 kilowatts. Therefore, this becomes 2 divided by 3 times 1.0, which is 0.66 recurring, or 0.7. I mean 67. So this is 0.67. Okay. The variation with the potential difference V of the circuit I in a component Y and in a resistor R are shown in the figure. Okay, so this is what we have, component Y. So it is I against V for component Y and resistor R. Use the figure to explain how it can be deduced that resistor R has constant resistance. Resistor R has constant resistance. I think we see it as a straight line which goes through the origin, and we can check that they said which is 20 ohms. We can check by taking values on the graph. So since it's a straight line, through the origin, then resistance is equal to V over I. So I will take a value from the graph. V, the maximum value is 10, and its corresponding value of I is 0.5. So this will be 10 divided by 0.5, which I think is 20 ohms. So you told the examiner it is a straight line, and you have verified that R is 20 by taking values from that line. The component Y and the resistor R in B are connected in parallel as shown in the figure here. Okay, so they're in parallel. So that means when the current reaches here, it divides. Part of it takes this path, and part of it takes the other path. So the total current I is going to be current through Y plus current through R. But the PD across is going to be the same as the EMF E. A battery of EMF E and negligible internal resistance is connected across the combination. Use the data from the figure to determine the current in the battery for an EMF of 6 volts. So the EMF is the same and the current is the sum. So we just look for 6 volts. So we look for 6 volts, and I will draw a line through 6 volts from the graph. 6 volts is here. The EMF is 6 volts, and is the PD across each of these components. So let me check out for the currents. The current through R is going to be, I think it is 3, and the current through the other one is, 0.3. This one is 0.2. So the current through 0.2 and 0.3, so we can find total current in the battery as the sum. So the current in the battery is going to be the current through Y plus the current through R, which is 0.2 plus 0.3. 0.2 is for Y plus 0.3 for R, which gives us 0.5. So the current is 0.5. The total resistance of the circuit for an EMF of 8 volts. We look for 8 volts and see the current. Total resistance for an EMF of 8 volts. let's first find, because we have to find the resistance of each. Resistance of, okay, let's first find the current when the EMF is 80 volts. So EMF is 80 volts. I think we are seeing that the current is the same. When the EMF is 80 volts, we are seeing that the current is 0.4 in each. The current is 0.4 in each for an EMF of 8 volts. So what is the resistance? So resistance of each, because the PD is the same and we are seeing the current is the same, so the current has divided equally. So resistance of each is going to be equal to a V over I, which is going to be V is the same, which is 8. Then the current is the same, which is 0.4. And that gives us 8 divided by 0.4, which I think it is 20. So the resistance of each is 20, but remember they are in parallel. So 1 over total resistance is going to be 1 over 20 plus 1 over 20, which is 2 over 20. So it means resistance in parallel, total resistance is going to be 20 divided by 2, which is 10 ohms. So the answer here would be 10 ohms. Okay. Remember, the total current is going to be 0.4 plus 0.4, which is equal to 0.8 amperes. That is the total current. If I have the EMF, I can find total resistance, because current is equal to EMF over total resistance. So I total is equal to EMF over total resistance. So that means total resistance can be the EMF, which is given as 8.0 volts, divided by total current, which is 0.8. So we can also check that 8 divided by 0.8 is automatically 10. So that will be method 2. This is going to be method 2. This was method 1. So you can just find total current. We see that total current is the same, but it is the sum of the two. Current in each is the same, 0.4, because we saw that at 80 volts, they were meeting at the same point. So it means the current in each is 0.4. So total current is the sum. Okay. The circuit in figure 6.2 is now rearranged as shown in the figure here. Now they are in series, the current flowing is the same, there is no splitting of current. Use the figure to determine the EMF E of the battery. The current in the circuit is 0.2. The current is the same, but the EMF E, this is going to be V across Y and this is going to be V across R. EMF E is going to be the PD across Y plus the PD across R, even though the current is the same. So let's go to the graph and find the current is 0.2. So when the current is 0.2, the PD across R is this one, that is 4, and the PD across Y is 6 at 0.2. At current of 0.2, the PD across R is 4 and the PD across Y is 6 volts. So the total is the sum. So the EMF here is going to be the PD across Y plus the PD across R, which is equal to, for Y is 6 and for R is 4, which gives us 10. So the EMF is 10 volts. Calculate the total power dissipated in component Y and resistor R. So we know that power is equal to the EMF times I, because they are in series. Total power dissipated is going to be just the power in the battery. So the EMF is 10 and the current is given as 0.20. which gives us 2.0 watts. The metal wire of constant resistance is used in an electric heater in order not to overload the circuit. For the heater, the supply voltage to the heater is reduced from 230 to 240. Time the percentage reduction in the power output of the heater. Percentage reduction of the power output of the heater. So we know that power is equal to V squared over R. It is the same heater, so the same resistance. So the reduction is going to be, for the first one, we shall say 230 squared over R. Then the other one is 220 squared over R. Then divide by the original, so that we get the percentage. So initial power is going to be 230 squared divided by R. Then the second value of power is going to be 220 squared over R. It is the same resistor, so the resistance is the same heater, so resistance is the same, 220 squared over R. Then the reduction is going to be 230 squared over R minus 220 squared over R. As a percentage, we now divide by the original P1. So the percentage, by the way, this one LCM is R, so this becomes 230 squared minus 220 squared. So percentage is going to be 230 squared minus 220 squared divided by R, again divide by the original, which is 230 squared over R. So R cancels, you remain with 230 squared minus 220 squared divided by 230 squared. So that is 230 squared minus 220 squared divided by 230 squared. So that is 0. So that is times 100. So times 100, which is 8.5. So this is 8.5%. 8.5. The percentage reduction is 8.5%. So we have a circuit here. An ammeter of internal resistance 5 ohms is connected to end A of the wire and to a contact C that can be moved along the wire. Determine the reading on the ammeter for the contact C placed at A. Of course, when we bring C at point A, it means we want the reading of the ammeter. When we bring C at A, it means the potential difference between A and C is the potential at A and C is going to be the same. So the potential difference is 0. Since current is going to be V over R, potential, there is no potential difference. PD is equal to 0. Potential difference is equal to 0, or there is no potential difference. So it means that current is going to be 0. Since there is no potential difference, so I is going to be 0. There is no potential difference. I is equal to V over R. Even though there is R, there is no potential difference between A and C if C is brought at point A. So it means this is going to be 0. Then at B is at the maximum point. If we take C at point B, it means AB is in parallel with a cell of 1.5 volts. AB is going to be in parallel with a cell of 1.5 volts. So it means the potential difference across AB is the same as the potential difference across 5 ohms. So we are saying potential difference AB is equal to 1.5 volts, which is going to be the PD across 5.0 ohms. But remember, PD is equal to IR. So we shall say 1.5 is equal to I, the current, times the resistance, which implies that I is going to be 1.5 divided by the resistance, which is 5. So this is going to be 1.5 divided by 5, that is 0.3. Use the circuit in B and the ammeter reading I in the ammeter reading I. Using the circuit in B, the ammeter reading I is recorded for different distances L of the contact C from end A of the wire. Some data points are shown here. So we have data points have been shown here. Use your answer in B to plot data points in the figure correspond to the contact C placed at end A. That was when it was at end A, L was 0 and I was 0. So the point is here, 0, 0. Then at B, L was 100 and I was 0.3. So we look for 100 and 0.3. I think 0.3, I will put the ruler. So I think this is the point. So that is the second point. So we have this point, we have plotted 0, 0, and we have plotted 100 and 0.3. Okay, so we have finished to plot. Draw a line of best fit for all data points and hence determine the ammeter reading for contact C placed at the midpoint of the wire. So we are going to draw a line of best fit. We are going to try and draw a line of best fit. So I'm going to put my ruler there and I try to balance these points. It is not easy because they are so much scattered, but I will try my level best. Okay, I've tried to draw a line of best fit. You can draw a better one. Try to balance the points 1, 2, 1, 2. Yeah, I've tried my level best. Although I know it is not the best. It may not be the best line. So we want to use this line and we are going to determine the ammeter reading for contact C placed at the midpoint of the wire. Midpoint is going to be at 50. Let me check 1, 2, 3, 4, 5. 50 is here. So 50 is here. That is 50 midpoint, and I'm seeing from my sketch, my graph, this is 0.11, 0.12, around 0.15. So I'm getting 0.15. I mean, no, 0.11, 12, 125, 0.125. Yeah. So if you are very accurate, I think you will get around 0.12 or plus or minus 0.05, around there, if you try to be very accurate. So mine has been 0.125, but I'm saying you can get between 0.12 plus or minus 0.05. Is it 0.05? No. 0.005, not 0.05. So you can get a value in that range, 0.12 plus or minus 0.005. So that's what I've got. You can also check with yours. Use your answer in Roman 2 to calculate the potential difference between A and B, between A and C for the contact placed at the midpoint. So we are still at the midpoint. Potential difference is equal to current times resistance. We have seen that the reading of the ammeter is 0.125 from the graph. I got my reading as 0.125. It was here in the center, but I said yours could be 0.12 plus or minus. So 0.125 is the current, and what is the resistance? Of course, the resistance of the wire was, the resistance was the resistance was, I think, 5 ohms. Yes, the resistance is 5 ohms here. So we just multiply this by by 5 ohms. So this will be times 5 ohms, or 5.0. So 0.125 times 5, which is 0.625, or which is approximately 0.63. If you get your value as 0.12, you may get 0.12 times 5, which is 0.60 volts. Explain why, although the contact C is at the midpoint of the wire AB, the answer in C is not numerically equal to is not equal to half of the EMF of the cell. So they are telling us that why is it that when the wire is here, why is it that when we bring C at the midpoint, the PD across the resistor is not equal to half of 1.5 volts? The PD across the resistor is not equal to half of 1.5 volts. I want you to note that when we bring a contact C somewhere here in the middle point, the resistance across AC is in parallel with the 5 ohms. So the resistance across AC is in parallel with the 5 ohms, so the total resistance here is not the same as the resistance across the remaining part, which will be C to B. So AC and CB are going to act as potential dividers. So the circuit is going to act as potential dividers, and the PD, the EMF of 1.5, is going to be divided in the ratio of the resistances, where the resistance across AC involves the 5 ohms, which are in parallel, and the resistance across CB is different. SC involves 5 ohms, so we get SC times 5 ohms over SC plus 5 ohms to get the total resistance here, which will not be the same as the resistance of the remaining part CB. So the potential divider divides the EMF of 1.5 in the ratio of the resistances, and the resistances SC and CB are not equal. So we are saying the circuit acts as a potential divider. The circuit acts as a potential divider. Acts as a potential divider. The circuit acts as a potential divider, and the resistance between A and C is not equal. to the resistance between C and B. As simple as that. If you want to look at that, it's like we are having two resistors. This is resistor AC, resistor CB, but then we have another resistor of 5 ohms here. Even if this resistor is identical to this, the total resistance here is not the same as the resistance there. So it means the potential divider does not divide the EMF equally, because SC is in parallel with another resistor of 5 ohms, yet CB is in series with the battery. So the EMF is not going to be divided equally. But if the one of 5 ohms was not there, then the EMF would be divided equally. So we can say, hence, if you want to add more, but it's just 2 marks, the 2 marks have already been catered for. The circuit acts as a potential divider, and the resistance between A and C is not equal to the resistance between C and B. You can go ahead and say, hence, the current in SC times the resistance is not equal to the current in the wire BC times the resistance of BC. So, or hence, the current in SC times the resistance in parallel is not equal to the current in BC times the resistance of BC. So they are not equal. So the reading cannot be the same. Okay. An electric heater is to be made from nichrome wire. Nichrome has a resistivity of 1.0 times 10 power negative 6 at the operating temperature of the heater. The heater is to have a power dissipation of 60 watts. When the potential difference across it is 12 volts. For the heater operating at its designed power, calculate the current. So we know that power is equal to I times V. So 60 is going to be equal to 12 times the current I. So just divide 60 by 12, which is 5. Show that the resistance of the nichrome wire is 2.4 ohms. We want to find the resistance. So we know V is equal to I times R. That means V is 12, I is 5 times R. So we just divide 12 by 5, which is 2.4. So this means R is 2.4 ohms. Alternatively, you can use power is equal to I squared times R. The power is 60, the current is 5, but squared times R. So we just divide 60 divided by 5 squared, which is 2.4. So R is equal to 2.4. Alternatively, you can use power is equal to V squared over R, where the power is 60 and V is 12, but squared divided by R. So we just cross multiply and say 12 squared divided by 60, which is again implies that R is 2.4 ohms. So any method leads to the same answer. Method 1, method 2, method 3. They lead you to the same answer. Calculate the length of nichrome wire of diameter 0.8 required for the heater. Length. So since it is length, we need an equation for resistance which involves length. Resistance is equal to rho times L over cross-sectional area. And we know that the area is equal to pi d squared divided by 4. So it means resistance is going to be equal to 4 times rho L divided by pi d squared. So we just substitute, or we make L the subject. I will make L the subject. L is going to be equal to R times 4 times pi d squared divided by 4 times rho. So R is 2.4. So that is 2.4 times pi times diameter of 0.8 times 10 power negative 3, and this is raised to power 2, divided by 4 times resistivity. They gave us resistivity as 1.0 times 10 power negative 6 in the question. So we have 2.4 times pi, then times 0.8 exponent negative 3, and this is squared, divided by 4 times 1 exponent negative 6. So that is 1.2. So L is 1.206 meters, or approximately 1.2 meters. A second heater, also designed to operate from 12 volts supply, is constructed using the same nichrome wire but using half the length. Same nichrome wire means same resistivity but half the length of that calculated in B. Explain quantitatively. Quantitatively, it means we have to be very specific. Explain quantitatively the effect of this change in length of wire on the power of the heater. So we have noticed that resistance is equal to rho L over area. So the length is now half. So resistance is going to be rho into a half L over area. So resistance is going to be a half rho L over area, where this rho L over area was the original resistance. Remember, power is equal to I squared times R. We notice that the resistance has been halved. So resistance is halved. Resistance is halved. Here we are being quantitative because we have to quote values. So we are saying the resistance is halved. When the resistance is halved, it means the power, actually when the resistance is halved, of course we know that the current is doubled. But let me not use this expression. Let me use the one of V and I, because V is remaining constant. So power is equal to V squared over R. V is constant. When the resistance is halved, the power is going to be doubled because they are inversely proportional. Or when the resistance is halved, the current is doubled. That means the power is going to be doubled. But if I use this one, resistance is halved, and since or from power equals to V squared over R, then the power is doubled. The power is doubled. Or resistance is halved, the current is doubled. Resistance is halved, the current is doubled, and from power is equal to I squared R, if the resistance is halved and the current is doubled, it means power is still doubled. The power is going to still be doubled. So you can explain in terms of this one where you use this equation V squared over R, or you explain in terms of this one where when the resistance is halved, the current is doubled, so the power is doubled. Okay. The figure shows the variation with applied potential difference V of the current I in an electric component C, as shown in the figure here. So it is an IV characteristic graph, which could be any material. Okay. State the reason whether the resistance of component C decreases with increasing potential difference. We see that the gradient of this curve is actually increasing, or the values of V over I are actually going to be increasing, or we see that I increases more rapidly as V increases, so it means the resistance actually decreases. So since it is not a straight line, we shall simply say that the resistance is the ratio V over I at a point. Resistance is going to be the ratio of V over I at a point, and we see that I is increasing more rapidly than V, as you see in this graph. I is increasing more rapidly than V. So since I increases more rapidly than V, then R increases. Since I increases more rapidly than V, then R increases. Then determine the resistance of component C at a potential difference of 4 volts. We want resistance. Resistance at any point is V over I. So let's look at 4 volts. I'll draw a line at 4 volts to see what is the current. No, 4 volts, I think it is this one here. At 4 volts. At 4 volts, the current is I think 2. At 4 volts, the current is 2 milliamperes. So this is going to be equaling to 4.0 divided by 2 times 10 power negative 3. 4 divided by 2 exponent negative 3, which I think is 2000. It's 2000. Component C is connected in parallel with a resistor R of resistance 1500 ohms and a battery of EMF E and negligible internal resistance. So now when the current leaves the battery, part of it goes through IC and part of it goes through R. So I'll have, it means total current is IC plus IR. But the PD is the same because they're in parallel, there is no internal resistance. So the EMF is the same PD across C is the same PD of R across R. On the figure, draw a line to show the variation with the potential difference V of the current I in resistor R. Because resistor R is constant and the PD across it is constant, I mean the resistor R is constant, it means as V increases, then it means I also increases uniformly. Therefore, this is going to be just a straight line. So this is going to be a simple straight line which will go through the origin. Because R is constant, the resistance R is constant, so it means V is directly proportional to R. So we are saying, since, where is it? It is here. R is constant, so V is directly proportional to I. So this is going to be a straight line through the origin. Line through the origin. Of course, it will go up to at the maximum voltage, which is 6 volts, and the current, which is, I think the maximum is 4 milliamperes. So it will go up to 6 volts, 4 milliamperes, because R is a constant, it's not changing, just a straight line. So I'll draw a straight line through the origin up to 0.64. So that will be our graph. Did they say we label it? Okay, there is no labeling. Hence, or otherwise, use the figure 6.1 to determine the current in the battery for an EMF of 2.0 volts. Hence or otherwise. Hence or otherwise. Hence means you can start from the previous part, or otherwise you can find another method. So since we want the current in the battery, we have seen that now current divides. The current in the batteries is IC plus IR. So the total current in the battery is the current through C plus the current through the resistance R. So we are going to use the graph to find the current. Remember, the EMF is going to be the same. The EMF is 2.0 volts and is the PD across C and also the PD across R. So we look for 2.0 volts, and I think 2.0 is here. So 2.0 volts, I think here it is in the center of this box. And here it is also in the center of this box. So the current for C, remember the graph there, the initial graph there was for component C. And for component C, I think this is 0. For component C, let me check. The scale here is 1/10, which is 0.1. So 1, 2, 3, 4, 5, 6, 7.5. So that is 0.7 and a half, 0.75. Then for the other one, we have 1.123, and it's almost here in the center. So it's around 1.35, if not 1.3. It is less than a half, so we can take 1.33 because it's less than a half. Here it was exactly in the center, but here it is closer to the bottom, so I can take 1.33. That is interpolation. Even if you take 1.35, you can't be penalized for that because you are actually making an estimate in the middle of the box. But if the box is large enough, you would see that is approximately 1.33. Okay, so we are saying we can take 0.75. So this is going to be for C, it was 0.75 plus 1.3. 5, is it 3.35? I guess 1. If I take 1.35, 0.75 plus 1.35, so that is, sorry, 0.75 plus 1.35, that gives us 2.1. So that is fine. We can take that one as 2.1. So we can take 1.35 or 1.33, but we'll all round off to the same value, 2.1. Okay. Then the resistor R of resistance 1500 ohms and component C are now connected in series across a supply of EMF 7.0 volts and negligible internal resistance. Use information from figure 6.1. Using information from figure 6.1, state and explain which component, R or C, will dissipate thermal energy at a greater rate. So they have been connected now in series. Remember, component C of course this is fixed. R is 1500 ohms. And now let's check 7 volts so that we find resistance of component C. 7 volts, 7 volts, 7 volts. We have 7 volts? Not at all. We don't have 7 volts here. Okay. We don't have 7 volts from the graph, but the resistance of R is 1500 ohms. And remember the PD across These, because they are connected in series, the resistor R of resistance 1500 ohms and the components are now connected in series across a PD of 7.0 volts, a negligible internal resistance. So if resistance of R is 1500 ohms, we can find the resistance C by first of all finding the current. Current is going to be no, this is resistance R. R is 1500 and the PD across is the EMF is 700 volts, 7.0 volts, which can be divided between 1500 and then component C. Use information from the figure. To state and explain which component R or C will dissipate thermal energy at a greater rate. Okay, so let's go back to the graph here. Because the PD is 7 volts, that PD is the sum of the PD across R and across C. So we are just going to look for a combination. 7 volts is equal to PD across R plus PD across C. So we are going to look for a combination which gives us 7 volts. Can I take 3 plus 4? 3 plus 4, that can give us 7, but yes, 4 plus 3, that gives us 7. The current is going to be 4 plus 3, that is 7. Is there any other combination? I think there is no any other combination we can take, because when I go beyond 4, 5 plus anything beyond 4, that will be above 7. So I take this. The current is going to be 2 milliamperes because the PD across, so 7 is going to be equal to 4. R is going to be 3 volts. And for C it is going to be 4 volts. Okay, so the PD across C is going to be 4 volts. Yes, from the graph, we have said that 7 volts is equal to PD across R plus PD across C. And we have seen from the graph that the PD across C is going to be 4 volts and the PD across R was 3 volts to get 7. So it means the resistance for C is going to be equal to resistance is equal to V over R, over I, which means V is 4 and the current was 2 milliamperes, that is 2 times 10 power negative 3, which was 2000 ohms. So for 1500 volts, R is 1500 volts, we are seeing that C from the graph is going to be 2000 ohms. It is not an easy direct thing here, but you can now write this in series. In a series, the current in R and in C is going to be the same. And we have seen it is 2 milliamperes from the graph. It is 2 milliamperes from the graph. But the PD across C is greater. But the PD across C is greater. Is greater than that across R. We have seen why. the resistance, we have seen that the resistance, actually the PD is 4 volts, yet for R it is 3 volts. But the PD across C is greater than that across R. So, because power is equal to IV, so since power is equal to IV, it means dissipation is greater. So power dissipated or power dissipation is greater. Power dissipation is greater in C. So power dissipation is greater in C. Okay. An electric heater is rated as 240 volts and 1.2 kilowatts and has a constant resistance. For the heater operating at 240, show that the current in the heater is 5 amperes. So we know that power is equal to I times V. The power is 1200, I is not known, and V is 240. So this is going to be 240 times I. So it means I is equal to 1200 divided by 240. 1200 divided by 240, which is 5. Then calculate its resistance. We can now just say V is equal to IR, or you can use an expression which has resistance for power. That is, power is equal to I squared R, or V squared over R. So this is going to be 240 divided by 5.0 times R. So it means R is going to be 240 divided by 5. 240 divided by 5, I think that is 48. The heater in A is connected to a mains supply by means of two long cables. There are two, as illustrated here. Total resistance is 4 ohms for the cables. The heater is rated to 41.2 kilowatts. The cables have total resistance 4 ohms. The voltage of the main supply is adjusted so that the heater operates normally at 240 volts. Use your answers in A where appropriate to calculate the potential difference across the cables. So potential difference is going to be I times R. So the current in the cables is 5 amperes times the resistance of the cables. Total resistance is 4. I think that is 20. Then the voltage of the mains supply. So this is the PD across the cables. But the heater, the voltage of the main supply is adjusted so that the heater is operating at 240. So the total is the sum. So voltage supply is going to be what is operating the heater plus what is between the cables. So that gives us 260 volts. Then the power dissipated in the cables. We know that power is equal to V times I. The power in the PD in the cables is 20, the current in the cables is 5.0, and I think that is just 100 watts. Use information from B to determine the efficiency at which power is transferred from the supply to the heater. That is, calculate the power dissipated in the heater over the power input from the supply. So power input, first of all, power input is going to be equal to the power of the heater, which is 1200 or 1.2 kilowatts, plus the power which is dissipated in the cables, that is going to be 100. That is the power input, which is 1300 watts. That is the power input. Then efficiency is going to be the power dissipated in the heater, which is 1200, over the input power, which is 1300. 1200 divided by 1300, that is 12 over 13, which is 0.92. 0.92. Okay. A student set up the circuit shown in the figure 7.1. The resistors are 15 ohms, 45 ohms. The battery is found to provide 1.6 times 10 power 5 joules of electrical energy when a charge of 1.8 times 10 power 4 coulombs passes through the ammeter in a time of 1.3 times 10 power 5 seconds. Determine the EMF. Of course, EMF, we have already defined EMF as energy transferred, um, energy transferred, energy transferred per unit charge. But here they have given us energy. The battery is found to provide 1.6 times 10 power 5 joules of electrical energy when a charge of 1.8 times 4 coulombs passes through the ammeter. So EMF is equal to energy per unit charge, which is going to be energy is 1.6 times 10 power 5 divided by charge 1.8 times 10 power 4. Energy per unit charge. So we press our calculator. 1.6 exponent 5 divided by 1.8 exponent 4. So that gives us 8.8 recurring, which is 8.9. Then the average current in the circuit, So we know that current is going to be charge over time. So the charge is going to be 1.8 times 10 power 4. The time is 1.3 times 10 power 5. 1.8 exponent 4 divided by 1.3 exponent 5. So that is 0.14. During the time for which the charge is moving, 1.1 times 10 power 5 joules of energy is dissipated in the 4 ohm resistor. Determine the energy dissipated in the 15 ohm resistor. The other one, 1.1 times 10 power 5 joules of energy is dissipated in 45 ohm resistor. Determine the energy dissipated in the 15 ohm resistor during the same time. So what expression relates energy to time? Of course, we know that energy is power times time, but power is IV, or I squared times power dissipated is I squared times R. So energy is power times time, which is going to be I squared R times time. So the first value of energy E1 is given as 1.1 times 10 power 5, which is equal to the current I squared times R, which is 45, times T. Are they in series? Yes, they're in series, so I is the same. Then the second energy E2 is going to be equal to I squared times the resistance, which is 15, and the time is the same. So I just divide the two equations. When I divide the two equations, I have E2 divided by E1, which is 1.1 times 10 power 5, is equal to I squared times 15T divided by I squared times 45T. So T cancels and I cancels. So E2 is going to be 15 over 45 times 1.1 times 10 power 5. So that is 15 divided by 45 times 1.1 exponent 5, which gives us 36666.6666 recurring, which is 3.7 times 10 power 4 joules. Suggest why the total energy provided is greater than that dissipated in the two resistors. Total energy provided is greater than that which is dissipated in the two resistors. In other words, where is the other energy? The other energy, I think they said it has an internal, the battery is found to provide that electrical energy. So a student sets up that circuit. If the total energy provided is not the same as what is dissipated, then the battery should be having some internal resistance. So we can say the battery could be, some energy is dissipated in the internal resistance of the battery. Some energy is dissipated, some energy is dissipated in the internal resistance, of the battery. Okay, some energy is dissipated in the internal resistance of the battery. Okay, next, define the coulomb. Of course, we know that coulomb is a unit of charge, and charge is equal to IT. Coulomb is, so 1 coulomb is equal to 1 ampere times second. So the coulomb will be defined as ampere second. Sorry, ampere times second, or ampere second. Ampere times second, that is a coulomb. A resistor X is connected to a cell as shown in the figure here. So the current is I, the length is L, cross-sectional area is M. The resistor is a wire of cross-sectional area A, length L. The current in the wire is I. Show that the average drift speed V of the charge carriers in X is given by that equation, where E is the charge on each carrier and N is the number of charge carriers per unit volume. Okay, so let's first of all find the total charge. We know that current is equal to charge, total charge over time, and the time is going to be equal to L divided by V. That is the length of the conductor divided by the drift speed V. So total charge, first of all, total charge is going to be the number of charge carriers per unit volume times the volume, which volume is cross-sectional area times L, then times the charge of one particle. So N times volume is total number of charge carriers, then times the charge of one particle, which is E. So it means now the current is going to be total charge, which is NALE divided by time, which is L times over V. So this means this will be NALE times V over L, and L cancels out. So it means I is equal to NAE times V, which implies that V is going to be equal to I divided by NA times E. Okay, a 12 volts battery with a negligible internal resistance is connected to two resistors Y and Z as shown in the figure here. The resistors are made from wires of the same material. That means they have the same resistivity. The wire of Y has diameter D, so this is D, and length L. The wire Z has diameter twice D and length 2L. Determine the ratio average drift speed of the charge carriers in Y over average drift speed of the charge carriers in Z. So we now know the formula, we are just going to divide. So V of Y over V of Z is equal to, the current is the same, so I'll just say I, N is the same, cross-sectional area for Y, E is the same, times I get the reciprocal. N is the same, they are from the same material, cross-sectional area of Z times E divided by the current is the same. So you notice that most of these cancel out. I cancels, N cancels, E cancels. So this will remain with A for Z divided by A for Y. Okay, but remember the area is pi d squared over 4. Area is equal to pi d squared divided by 4. So it means V for Y over V in Z is going to be pi. For Z diameter is twice d, so this is going to be pi into twice d squared over 4. Divide by, I get the reciprocal, 4, no, yes, AZ over AY, okay. Then divide by area of Y, which is going to be 4, divide by pi, diameter is d, and that is squared. So 4 cancels, pi cancels, we remain with 4d squared over d squared, which gives us the ratio as 4. So that ratio is 4. Then show that resistance of Y over resistance of Z is equal to 2. We know that resistance is rho L over area, and area is pi d squared over 4. So this is going to be 4 rho L over pi d squared. That is the resistance. So we shall have two equations. Resistance for Y is equal to 4 rho. The length of Y is L divided by pi d squared. That is the diameter of Y is d. And the resistance for Z is going to be 4. Rho is the same because they are from the same material, but the length here is 2L. Divide by pi, the diameter is twice d, so this is twice d and this is squared. So we now find a ratio. The ratio is going to be equal to, we are dividing 4 rho L over pi d squared times, I'm getting the reciprocal because it is division, times times pi into 2d squared divided by 4 rho times 2L. So pi has cancelled, 4 rho has cancelled, L has cancelled. So I remain with, in the numerator I have 4d squared divided by, in the denominator I have d squared times 2, which is twice d squared, which gives us 2. So the ratio there is 2 because d squared cancels out, 4 over 2 is 2. Determine the potential difference across Y. Potential difference across Y. It means if I want the PD across Y, I may need the current through Y times the resistance of Y. And what is the current? And we know that the current is equal to the EMF over the total resistance, R total. The EMF is 12, and total resistance is going to be resistance of Y plus resistance of X, of Z. But remember, we have that resistance of Y is twice resistance of Z. Resistance of Y is equal to twice resistance of Z. So it means we can remove, since what is 12? 12 is the total PD, the total EMF. We have that resistance of Y is equal to twice resistance of Z. That means because I want the answer to be in terms of Y, I'm going to remove Z. So it means resistance of Z is going to be resistance of Y divided by 2. So this is going to be 12 divided by resistance of Y plus resistance of Y over 2, which gives us 12 divided by LCM is 2 in the denominator. So you have 2 divided by 1, that is twice Ry plus Ry. This gives us, the 2 goes up, so it becomes 2 times 12 divided by, in the denominator you have 3 Ry. That is going to be the current. This is now the current. 2 times 12 over 3 Ry. So I substitute in the expression. So it means the PD. So we have that the PD across Y is going to be the current, which is 2 times 12 over 3 Ry, then times the resistance, which is Ry. So we notice that Ry cancels out. So Ry cancels out. You remain with the 2 times 12 over 3, which is 24 divided by 3, which is going to give us 8. So this is 8.0 volts. You can find this in a more simpler way, but that is the simplest I can have. Then a 15 volts battery with negligible internal resistance is connected to 2 resistors P and Q as illustrated here. The resistors are made of wires of the same material. That means the resistivity is the same. The wire of P has diameter D and the wire and length 2L. The wire of Q has diameter 2D and length L. The resistance P of P is 12 ohms. Show that the resistance of Q is 1.5 volts, ohms. So number 1, did I miss out something? Yes, I missed out something. Sorry. Determine the ratio power dissipated in Y over power dissipated in Z. So power is equal to I squared. Power is going to be I squared times R. And the current is the same because they were in series. So the ratio is going to be I squared times R of Y divided by I squared times R of Z. And the I is the same. We have seen the ratio Ry over Rz is 2. So this is just going to be 2 because this one cancels. And that gives us 2. The ratio there is 2. You can use V squared over R. You can check that one. V squared over R. Maybe I can again check that one. So the ratio will be V. Of course, the PD is going to be divided. So this will be V for Y squared over resistance of Y divided by V for Z squared over resistance of Z, which is going to be V for Y over V for Z, and this is squared, times, we get the reciprocal, remember. That will be R for Z over R for Y. Remember, R for Z over R for Y is a half, is the ratio of which we got as a half. V for Z, we got the potential difference across Y was 8. Then it means that the potential difference across Z is going to be 4 because the sum is 12. So this is going to be 8 over 4, and this is squared times a half, which is going to be 2 squared times a half, which is still 2. So that is method number 2. Okay, so here show that the resistance of Q is 1.5 ohms. Okay, so to start with, the space is very small, I will divide it. So resistance is equal to rho L over cross-sectional area, but remember area is pi d squared over 4. So this is going to be 4 rho L over pi d squared. 4 rho L over pi d squared. So we are going to come up with 2 equations here. For P, resistance for P is going to be equal to 4 rho. Length for P was 2L, so this will be into 2L. Divide by pi, the diameter for P was D, so this will be pi D squared. And for Q, we shall say R of Q is going to be equal to 4 rho, because it is the same material. Its length is L. divide by pi. Its diameter was twice d and it is squared. Okay, so we are now going to compare the two equations. We want resistance of Q, so I'm going to divide the two equations. Resistance of Q divided by resistance of P, which is 12, should be equal to 4 rho L over pi into 2d squared times, I'm getting the reciprocal because I'm dividing the two equations. So that would be times pi d squared divided by 4 rho into 2L. So some things can cancel out directly. I will change the color to cancel out things. 4 rho cancels, L has cancelled, pi has cancelled. So we now have that RQ is equal to, in the numerator I have d squared over I have 4d squared times 2, there's a 2 there, then times 12, I'm cross multiplying. So d squared has cancelled, so I now have 12 divided by 8. 12 in the denominator divided by 8, d has cancelled out, d squared has cancelled out. So we have 12 in the numerator divided by 2 times 4, which is 8. So this gives us 1.5 ohms. Okay, that's 1.5 ohms. Calculate the total power dissipated in the resistors P and Q. We need total resistance then, if we are to find total power. Because total power will be V squared over R total. Total power is going to be V squared over R total, where this will be EMF over total resistance. And total resistance, remember they're in parallel. One is 12, one is 1.5. So total resistance is 12 times 1.5 over 12 plus 1.5. Product over sum for resistors in parallel if there are only two. So it means the power is going to be the V or the EMF, which is 15 squared, divided by total resistance, which is 12 times 1.5 over 12 plus 1.5. So I'll just press my calculator. 15 squared divided by 12 times 1.5 divided by, open another bracket. Of course, even if I don't open another bracket, I'll just say divide by 12 plus 1.5, that is 13.5. So that is giving us 168.75. 168.75, which is approximately 170 watts. Determine the ratio average drift speed of the charge carriers in P over average drift speed of the charge carriers in Q. Okay, so of course the current, we have seen that the current divides because they're in parallel. So I'll first of all find the current in P. Current in P is going to be the P is the same 15, the resistance for P is 12. And the current in Q, the P is the same 15, the resistance is 1.5. Okay, but then drift velocity is equal to I over never. So that is going to be N E times A. Okay, they are from the same material, so we can assume that N and E are going to be the same, but the areas will not be the same. So drift velocity for P over drift velocity for Q is going to be equal to, for P, current in P divided by N area of P times E, then divide by, I will get the reciprocal. That will be N area of Q, E divided by the current of Q. I've just got the reciprocal when dividing the two equations. So N cancels, E cancels, so we don't need those. So we are only remaining with this ratio as being current in P over current in Q times area of Q over area of P. Remember, area is pi d squared over 4. pi d squared over 4. So we are now just, since we have IP, we have the current in P and the current in Q, we can just now find a ratio. So the ratio is going to be equal to IP is 15 over 12 divided by IQ, which is 15 over 1.5, times the area of Q, which is pi. Let's check, the diameter of Q was twice d. So the diameter of Q is twice d, so the area is going to be pi into twice d squared over 4 divided by the area of P, which will be pi. The diameter of P was just d. So divide by pi d squared divided by 4. Okay. So we notice that pi cancels, 4 cancels. So pi cancels, 4 cancels. So just press our calculator here. We have 15. 15 divided by 12. Then divide by 15 divided by 1.5. So that's 1 over 8 times. Here we have 4d power 3, which is, 2d squared, that is 4d squared divided by d squared. So 4d squared divided by d squared, so d cancels, d squared cancels. So you have 1 over 8 times 4, which is going to be 0. I think that is 0.5. 4 divided by 8, that is 0.5. So the ratio is 0.5. Okay, let part 2 stop here. We shall start from here in part 3. Have a blessed day. Bye bye.